Please join me in welcoming Ariel Ortiz, who will be presenting the perils of inheritance, why we should prefer composition. Thank you.
Hi there. Just a quick notice, this is where you can download the slides. I prefer to put them right now because I oftentimes finish the presentation and don't have a lot of time left. So if you think you might need it, there's a QR code and there's the shortened URL there available, okay? So I'll leave it a few seconds. Thank you very much for coming to this talk. As the presenter just said, my name is Ariel Ortiz. I come from Mexico. I work at the Tecnológico de Monterrey, the Monterrey Tech, which is a private university in Mexico. It's one of the most important private universities in the southern border for here. And I'm going to talk on this topic that has to do with the perils of inheritance and why we should prefer composition. So yesterday I was actually practicing a little bit my presentation, and I really heard the name of the presentation out loud and says, well, this really sounds like clickbait. I could have just as well put as a title the 4 dangers of inheritance and why you should avoid it, and you won't believe number 3 or something like that. But it wasn't really my intention to make it a clickbait, so I apologize if it sounds like that. I'm a full-time faculty member. I've been teaching computer science for more than 30 years. And I've been using many languages. Python is one of them, and it's one of the ones that I actually prefer to work with. But specifically using Python, I've used it in classes like data structures and CS1 and even web development and compiler construction. So we've had a chance to actually work pretty nicely with Python. I started working with Python version 2.0. Somewhere, I think around, was the year 2001. So we've been able to see the evolution of the language in the last 2 decades. So let's go and start talking about what we care about in this presentation. So we need to define 2 specific concepts. One is inheritance, and the other one is composition. So let's quickly look and see what they are. In the case of inheritance, we have this kind of relation. We have 2 classes. One we referred as the base class. The other one is referred as the derived class. Let me see if we can put a little pointer here. So these sometimes actually come with different, with other names. Sometimes the base class is referred as the superclass, and the derived class is also referred as the subclass. So this is inheritance. Basically, you have a certain amount of attributes, could be methods or could be instance variables, and all of them are actually inherited to the derived class. So instances of this class basically has everything that this one has, plus you can add some additional information if you want, or additional attributes. Composition looks like this. Instead of using a triangle in the UML notation, we use a diamond, and the one who's containing the other object, we call it the composite. Also, it might be referred as the wrapper. And we have the component. This is what we are actually making or building our object with, okay, the composite object. So if this one is known as a wrapper, some people actually call this the wrappee. So this is composition. So how does this look in Python? It's very straightforward. Probably most of you are fairly familiar. So here we have a syntactic example of how you would look at inheritance. Here you have a class called vehicle, and you have a bicycle. So in this case, you say that a bicycle is a vehicle. So in the case of inheritance, you have an is-a relationship. In the case of composition, here you have a class called engine and a class called car. And we say that a car has a an engine. So in that case, we're having a composition or a composite relationship there, okay? So here, as you can see in the dunder init method, we're actually calling the initialization, the construction of the engine. That information or that reference to that object could also be sent as part of this method, okay? It really depends how we want to implement it, but that's the general idea between these two concepts, inheritance and composition. Okay, so this specific design suggestion or design principle or guideline, whatever you want to call it, which is favor composition over class inheritance, this actually appeared many years ago, more than 2 decades, and it was made popular in this book called Design Patterns, Elements of Reusable Object-Oriented Software. This was written by the Gang of 4, as it was actually called. This group of 4 people were Erich Gamma, Richard Helm, Ralph Johnson, and John Vlissides. So in the first chapter of this book, they set certain suggestions or guiding principles that allowed them to explain how they went on presenting this catalog of design patterns. And one of the suggestions that they made from the very start was should favor object composition over class inheritance. And this was an important situation because at that moment, most of the people were using inheritance almost for everything that had to do with reuse. And composition was a concept that not many people knew. Now, interesting thing is that even more than 20 years afterwards, most people tend to use inheritance as one of the main and first mechanisms for having the opportunity to reuse code. And since those decades ago, it has been actually recommended that you can use inheritance, but you should favor composition at the very beginning if that's possible, okay? So specifically, they presented here 2 mechanisms of actually having code reuse. They refer to one of them as the white box reuse and the other one as the black box reuse. And white box, in this case, probably a better term would be crystal box. We can actually see the details of the implementation, and this happens when we use inheritance. The derived class typically has access and can see many of the details that are related to the superclass or the base class. So here you have a lot of information available, which many times might not necessarily be something that you really want to know. And in general, we prefer to use black box reuse, and this happens when you use composition. Black box basically means that you have your object, you only see the external part, which happens to be the interface, and the internal details of the implementation is something that is actually kept as a secret, not because we don't want people to know how it's done, but because it's irrelevant on how we, or the information that we need to know in order to use the object successfully. Okay, so for example, if we drive a car, fortunately, we don't need to be some sort of mechanical engineer wizard to know how the internal car actually works. We can just basically interact with the interface of the car. And fortunately, not knowing how it works is really a blessing, because otherwise, I think most of us wouldn't be able to actually drive a car. So the same thing happens here with our objects. We try to encapsulate and hide most of the details, not because we're bad people and we don't want people to see how it's made, but it's just a situation that makes it simpler just to use if we can just eliminate or obviate some details of the implementation and just go and use our object through its interface. So inheritance does have its advantages. So first of all, it's probably the easiest way to reuse code. If we're using Python, well, you just need to declare and define your class, and you put a list after the name of the class, the list of the class or classes that you want to inherit from, because you actually have the option of having multiple inheritance in Python. So it's very, very easy to actually do it through this way. Okay, so that's probably the main advantage. Secondly, once we inherit, the subclass or the derived class is allowed to add new behaviors that didn't exist in the superclass, and it can modify behaviors that already exist or just add new ones if that's what we require. But here comes the dark side of this, okay? So some of the disadvantages I actually establish here for that are some sort of drawbacks. The relationship between a base class and a derived class is statically fixed. Now, this is technically not true in Python because Python is really dynamic in nature. So it is possible to actually, at runtime, actually create some inheritance relationships that are decided at that very moment. But in most object-oriented programming languages, once you establish who is your base class of a certain other class, derived class, you can't change it, okay? This is something that typically is fixed. It's decided at compile time if you're using a language like C++ or Java. And if you wanted to inherit from another class at runtime, that's something that typically you won't be able to do. So this is a drawback, okay? Secondly, inheritance actually supports weak encapsulation and fragile structures. We're going to see an example where this happens. Sometimes because you know the information that or the attributes that you're inheriting from, you can end up using them in some ways that are not necessarily compatible on how the designer of the base class wanted. And sometimes you might end up having name collisions in the derived class. For example, you might add a new method in the derived class, and suddenly the author of the base class suddenly wants to use that same name for a totally different purpose. So you enter in some possible clashes with names there. So that might result in a very inconvenient situation if it happens. Thirdly, a derived class inherits everything, even things that we don't need or we don't want. Joe Armstrong, who is the creator of the Erlang programming language, he actually passed away a few days ago. But a few years ago, Joe Armstrong basically said that one thing that he didn't like about object-oriented programming is that you get many things that you don't necessarily need. So he said, well, if you want a banana, unfortunately, sometimes you have to have the gorilla that's grabbing the banana and the whole jungle, okay, in order to reuse it. And so that's not necessarily something that you want to have in practice in many circumstances. So if you use inheritance, unfortunately, that's what happens. And as a fourth point here, as I mentioned before, you can have changes in a base class in the interface. This will impact all its derived classes. So as I explained, if you certainly have a new method name or whatever in the base class, well, automatically every class that inherits from that one might be impacted, okay? So let's have a look at a code example. The full source code, if you want to test it yourself later on, is available in GitHub, so just get a hold of the slides and follow the link that is available here. It's actually in GitHub, the information, the different source, and it basically represents the history. The commits represent the history of the way that I'm going to show it just in a moment. So if you check the source code, please check the history of commits and check them in order so you can see basically the same steps that I'm going to be taking here, and you can recreate basically everything that we're going to look just now. Okay, so what are we going to do? We're going to implement a simple linked list. Okay, so if you've ever taken a data structures course, this might bring you good or bad memories. It depends how well it went. So we're going to define here a dunder init method to initialize our linked list. We're going to have an insert and insert all methods. Insert is going to allow us to insert a certain value, one individual item or value. Insert all is going to take an iterable object, and it's going to insert all those elements inside our linked list. Remove is going to allow us to eliminate or remove the element that is at the beginning of the list. In this case, it's as we explained a moment ago, it's a LIFO list. It means that's last in, first out. So it really works more or less like a stack. So what does this mean? That the most recent element that was inserted is going to be the one that goes out first, okay? So it's a last in, first out policy that we're going to be implementing. So removes the most recently inserted element. Clear eliminates all the elements of the list. And then we have these other dunder functions. This one allows us, iter, allows us to iterate over all the elements in a sequential fashion. str gives us a string representation of our list. We're going to use basically the same notation that are used in standard arrays or lists in Python. And we have len that determines how many elements we currently have. So we're going to see how, in this case, we have this other class called InsertCounter. And this one is going to be responsible of adding two new, well, not two new methods, actually overriding two existing methods, insert and insert all. We want to have here a class that only has a count of how many elements have been inserted so far, okay? We don't want the exact number of elements contained in the class. I mean, this is actually determined by len. This one is going to count only the elements that have been inserted. Some of them might have been removed later on, okay? But we only want a count of how many times we actually called the insert or the insert all. Counting exactly how many elements so far have been inserted without any regard on if they have or not been removed so far. And the only new operation that we're adding is this one called counter. And we're going to inherit from this one here. So this is a first example using inheritance. And this allows us to basically have, for free, the operations that are not listed over here. So remove, clear, dunder, iter, dunder, str, dunder, len, all of them are inherited automatically. We don't need to provide their implementation. So this is the code. First of all, for linked list, okay, so we have a nested class called node that represents individual nodes of our linked list. Okay, we have our init, which creates here the start of our linked list. We're using here a header or sentinel node. I'm not going to go into the details exactly how the linked list works, but in general, in a very high level, we're just inserting elements at the very beginning of the list, and we're removing them exactly from that same place. So insert does that, and we have this instance variable called length. We increment it every time we do an insert. And then the other insert all operation takes the iterable object so we can traverse it using a standard for instruction. And once again, we do the corresponding updates of the references that we use to insert elements at the top. Actually, because we insert them in the same order in which they are presented in the iterable object, at the end they end up actually being inserted in reverse order, okay? Because that's basically how a LIFO last in, first out policy data structure works, okay? Here's remove, just checks that we don't have an empty list. Otherwise, we remove that first element, we decrement the length counter, and we have the other support operations, clear, iter, str, and length, okay? So let's have a look at the subclass. Okay, we have the insert counter, and as we explained, we're using inheritance, so we indicated here that we're inheriting from that particular class. We have init, in which we call the init of the superclass so that corresponding instance variables from the base class actually get created and so on. We have this special specific instance variable for this subclass that it's called counter. We start in 0 and we're going to increment it, as you can see here, with 1 every time we insert one element. And if we want to do an insert all, here we actually have the iterable because we're going to need to iterate twice over the same object. Here we use this t method that actually allows us to create 2 clones of the same iterable object. And we use the first one to call the insert all from the superclass. And here we just use a generator expression to count how many elements effectively we have there. We sum them up together and we add them here. Okay, so this one adds 1 to every element that we add one at a time, and this one adds the number of elements that it requires according to the length of the iterable object. Okay, and we have a property here called counter. When we call this, it just returns what is in this internal counter object to indicate how many inserts we've done so far. So here's an object, here's an example, excuse me, where we create an instance of InsertCounter. We insert once, we insert using all, which are 5 elements that we have here. We remove it once. So as you can see, the content of the list is printed here. Okay, and we're going to see the length and the corresponding counter here. So when we run this, let's see. Okay. Okay, the contents are, as you can see, 23, 16, 15, 8, 4. We eliminated the 42 because we removed it over here. Remember, we removed the last one we inserted. So it says correctly that we have a length of size 5 and the value of counter, which indicates how many individual elements we have inserted, is 6, which is correct. Okay, but now let's assume that the author of this module here does a code review and suddenly realizes that the insert and the insert all, basically they duplicate the same code. It's basically identical. All this part here, if you look at it, it's identical what is inside the 4. So the author can actually say, yeah, let's eliminate this and let's call self.insert, which is the operation that we have up here. Okay, just sending here the expected value. Oops, this is self. Okay, so now when we return to our subclass again, and we run it, suddenly we realize that something happened to the counter. Instead of being 6, which is the correct number of elements that we have inserted, it's now 11, okay? So what happened? Well, what actually happened here when in the base class you did the insert all, you sort of thought that calling this insert was calling this particular implementation insert, but actually that's not what happened because we're doing it in a subclass. This insert is actually a call, polymorphic call, to the corresponding insert of the derived class. So what I want you to understand very, very clearly is that we did not modify the client code, or in this case, the derived code. We are basically still inheriting as usual. But a change in the original base class actually made the derived class actually work differently. Okay, and that's something that, well, typically you don't want to happen. And it all happens here that we're actually calling here from the insert all, we're calling insert, which will actually call mine, which at the same time will call the inherited one, the inherited version over here. Okay, but it still will do the code that we provided over here. So it's producing wrong results. So how can we correct this? Well, we can use the other technique, which is known as composition. So what happens here is that instead of inheriting from the linked list, we receive the linked list as a parameter to init. And every time that we want to do an operation like insert and so on, we delegate it to the component object. In this case, what we're calling here the linked list instance variable. Okay, so when we call insert, we delegate it to the linked list. But we have to do that with every single method as well. Okay, the only, of course, that is unique here is the counter. This one still works the same, but even the other operations, if I still want to support the full interface that we had from the original class, that was the base class in the previous example, we need to provide one by one all the methods that delegate to the corresponding operations carried out by the linked list itself. Now, that's, of course, a little bit more of a problem. We have the same client code over here, but when we run this, we can see that we return once again to the correct results. So now changes in the implementation of the superclass do not affect this class, which is not inheriting anymore. It's actually using composition, okay? Now, of course, there's a lot of work here on just doing the delegation. As you can see, we needed to repeat every single method because we're not inheriting them, so we need to explicitly provide them. So an alternative here is a really nice package called Forwardable, which does a lot of the work for us. So how you use it is basically you define your class that is a composite. You put the forwardable annotation with parentheses here, and you define, or you use this function called fdelegators. And here you're saying that whenever we have any of these methods in this class called remove, clear, iter, dunder, str, dunder, len, it will automatically delegate it to that. So we don't need to explicitly write the code for that. We only need to provide the things that do not exclusively do delegation, but do something additional to that, okay? So once again, that reduces considerably the size of the class. And when we run this, it still works as expected, okay? So that's a quick way of carrying on composition without having to write too much boilerplate code, okay? The whole trick is letting the forwardable module do most of the trick. Okay, so what did we do? Just a moment ago, we created here this class called InsertCounter. And we want to reuse some of the functionality from linked list, but instead of inheriting, we use composition. Okay, so in this case, this class becomes the composite, and this is the component here. Okay, and as you can see, it works, and we get all these methods remove, clear, and so on for free, or more or less freely if we use the corresponding forwardable package. Okay, so what are the advantages of using composition? Well, we can have configurable implementations at runtime because we send as a parameter during initialization the object that we want to use as a component. We can change those dynamically in any moment, so that gives us a lot of flexibility. Supports good encapsulation and adaptable structures because we're only using the interface of the component. If at some point something changes in the interface, it only actually affects the code of the composite, so the problems or the errors that might occur are clearly contained there, not in the client. Interface changes have a limited ripple effect. Once again, it only affects internally the composite object. So once again, changes are fairly controlled. They might occur. We might have some errors, but they're more easy to identify and correct. Composition allows a composite class to have relationships with many component classes, not only one. So this is actually the basis of a pattern called Facade. So the composite of it can actually have several components, and we, as a facade, we can actually simplify the way that clients actually access all these components there, okay? We do have some disadvantages when using composition. So as we saw, typically we need a little bit more code when using inheritance, so that can be an issue. But once again, the package that we saw, forwardable, allows us to minimize a little bit of that. And this is probably the main problem here. It's typically more difficult to read than inheritance. So we have to be careful that if somebody looks at the code, it might not be immediately obvious that we're using and how we're using composition, okay? So when do we use inheritance? If you are the author, the base class, and the derived class, and you're working in the same module, the same package, that's fine. You can see how your superclass is actually defined, so there's not a big issue. So if that's the case, feel free to use inheritance. If you're using classes that actually are designed to specifically support and they document it correctly, the use of inheritance, that's also a good way of following through. And some last things to note here. First of all, inheritance is not wrong. I mean, don't feel guilty if you use it. You do need to use it in many circumstances. It's just a matter of using it in the correct way, okay? Only use inheritance when a new class really does define a subtype, so it means that you have an is-a relationship instead of a has-a. Inheritance and composition are not competitors. They usually complement each other, so just know how to use each of them correctly. And if you're going to define a class that will be allowed to be subclassed, just make sure that you document it correctly. So here's an example from the JSON encoder. I'm not going to look at it now because we're almost out of time, but it shows clearly what happens or how you could document a class that is actually designed for inheritance. Okay? And there's also this part known as the Liskov substitution principle. LSP is one of the solid design principles. Basically says that functions that use references to base class objects must be able to use objects of derived classes without knowing it. Okay? In other words, if it looks like a duck, quacks like a duck, but walks on wheels, you most likely have the wrong abstraction there. Okay? So you have to make sure that subclasses actually work as the corresponding superclass should work. Okay? So as a conclusion, should we use inheritance or composition? You might know this girl from memes. She actually speaks in Spanish. She says, ¿Por qué no los dos? Why not both of them? Okay? Thank you very much.